Hello again to FlippedHarber for Calculus. In this video we'll be learning how to take derivatives using the chain rule. Our objectives for this video are to learn how to apply the chain rule when taking the derivative. Our outline for this video, we'll take a look at how to take the derivative of a polynomial to a power. And when I say this, we're going to do it the hard way. Okay? Then we'll take a look at what the chain rule is. And then we're actually going to take the same derivative using the chain rule, and it turns out that it's an easier way. Then we'll take a look at another example of the chain rule. We're going to learn how to take the derivative of an exponential function, a to the x, which is a lot like e to the x, but our base isn't e, it's some other number. We're going to talk about parametric curves, what the heck they are. Then we'll learn how to take a tangent line to a parametric curve, and I want to just remind you of an equation that we're going to see in this video because it's really going to become important later in the class. Alright, so let's take a look at taking the derivative of this trinomial, x squared plus 3x minus 1, that is squared. So the way we're going to have to deal with this right now is we're going to have to do this algebra inside the square brackets. We're actually going to have to square our trinomial. So we're going to take the derivative of x squared plus 3x minus 1 times x squared plus 3x minus 1. So when I do that, I get x to the fourth plus 6x cubed plus 7x squared minus 6x plus 1. Now that is not the derivative yet. That is just what the heck the stuff inside the square brackets are. And now I am going to take the derivative of this. So now I'm going to take the derivative of this new polynomial. And I get 4x cubed plus 18x squared plus 14x minus 6. Now, not real difficult algebra, and really not a difficult derivative at all. It's just the power rule and the addition and difference rule. So you're probably going, that wasn't that hard. But what if that square had been a cubed or a fourth power or a fifth power? The more power we've got, the more difficult this is going to be, the bigger this polynomial is going to get. It can turn difficult really, really quickly. Okay, so we're going to look at a new way to take this derivative called the chain rule. Now, this is probably the most important rule when we're learning how to take the derivative. The reason I say that is, we've learned the power rule, the product rule, the quotient rule, all these trig rules. But the chain rule is so important because we're going to be using it almost all the time now. Because we've really been, keeping some blinders on, and we've only been taking these products and everything with just really simple functions. So now we're going to have more complicated functions where it's not just the sine of x, but it's the sine of x squared, or the e to the x squared. So this is really an important rule when we have a function of a function. So if you stop and remember this from your pre-calculus and your Algebra 2 days, we're talking about plugging a whole function, g of x, into a bigger function, f of x. And the chain rule lets us deal with that. And the way we do that is we take the derivative of f, leaving g of x plugged inside, and then multiply by the derivative of g of x. Now that looks a little bit weird. I always like to think of it as a quote-unquote inside function and an outside function. Best way to find the inside and the outside is to look for parentheses that are already there, that are given, or where could I put parentheses? And those parentheses help me identify what is the quote-unquote inside function and the outside function. Once I've identified my inside function and my outside function, what I do is I tell myself, okay, take the derivative of the outside function and leave the inside totally alone. Leave the inside alone for that first step, and then multiply by the derivative of the inside. So, best way to learn this is to take a look at some examples. So let's take a look at that polynomial squared from earlier. My outside function is literally what's going on outside the parentheses. My outside function is that square. My inside function is the polynomial itself. Literally, I've got to set of parentheses here already. What's outside the parentheses? What's inside the parentheses? So the way that I do this derivative using the chain rule is I bring that 2 out in front. I follow the power rule on that outside function. And again, I follow the rule and I'm going to deal with everything in the next step when I get to the next step. Just kind of blindly follow the rule right now. Deal with the square, leave the inside alone. Then multiply by the derivative of the inside. Multiply by the derivative of x squared plus 3x minus 1, which is 2x plus 3. That's not a difficult derivative. The power rule was not a difficult derivative. Putting them together, very new novel way for us to do this. But now I just have to simplify. I'll go ahead and multiply my 2 in, and I do have to multiply these two polynomials. What I end up with is 4x cubed plus 18x squared plus 14x minus 6. I took the derivative way up at the top. The derivative was here. Don't take the derivative again. From that point down, I'm just doing algebra. So don't try to do the derivative again. I've seen a lot of kids try to take the derivative again. They didn't realize you already took the derivative in that very first step. So don't do it again. All right, let's take a look at another example of the chain rule. Now, I always like to step back from a function and think, okay, everything that's going on here, definitely got some chain rule going on or else I wouldn't have it in this video. But I've also got a product right here. So I've got to use the product rule. And I see one set of parentheses. I see a set of parentheses around the x cubed. But I'm going to draw in another set of parentheses here, probably ones you didn't think of. I'm going to put the 2x plus 4 in parentheses. Now what that does is that identifies my outside function, e, and my inside function, 2x plus 4. So I've got to follow my product rule. I've got to follow my e rule. I've got to follow my sign rule. And I've got to follow my chain rule. So there's a lot going on here. But just follow each rule. First of all, big picture, I've got a product. So I take the derivative of the first factor, that e. So the derivative of e to some power is the exact same thing. Multiply by the derivative of the inside. So this 2 right here comes from the derivative of 2x plus 4. Multiply by the second factor. So there's no derivative involved there. It's there because of the product rule. It's just sitting there waiting for its turn to do something. Plus, now this e to the 2x plus 4 is the first term. It's just sitting there. I didn't take the derivative of it or anything. And I multiply by the derivative of the sine term. The derivative of the sine of something is the cosine of the exact same thing. So cosine of x cubed times 3x squared. That's the derivative of the inside. Now I can try to simplify this. I can factor out an e to the 2x plus 4. I still have 2 sine of x cubed as the first term plus, and I move that 3x squared up front, so it's 3x squared cosine of x cubed. Not much else I can do with that, so I just let it sit, and that is my derivative. Now let's learn a new rule here, the derivative of a to the x. So this is like our e to the x rule, but the base number is not e. So that base number could be 5, could be 22, could be pi, any constant other than e. And we find out that the derivative of a to the x is equal to a to the x. So it's part of its own derivative times the natural log of a. Now if I try to apply this rule to e, what I end up with is e to the x natural log of e. The natural log of e is 1, so it just doesn't bother to use this rule with the e. So to take a look at an example, the derivative of 5 to the x is equal to 5 to the x times the natural log of 5. Let's throw a little bit of a chain rule in there, the derivative of 4 to the 2x. So again, I'm putting my parentheses around the power. So I get 4 to the 2x times the natural log of 4. So that's the derivative of 4 raised to some power times, and that 2 is the derivative of our inside. Now that 2 cannot multiply the 4 out front. It cannot multiply the natural log of 4. Okay, let's talk about parametric curves. A parametric curve is one where both the x and the y are written as functions of a third variable. Usually we do this where x is a function of t and y is some function of t. Now I've decided to go ahead and use the parametric equation x equals 4 cosine t, y equals 4 sine t. Now what this will create, and we can actually make our calculators do this if we put them in the right mode, we get a nice circle. So this is a great way to take a circle and write it as a function. A circle cannot be a function because it doesn't pass the vertical line test. But these two parametric equations are both functions. So we get to do some things with them when we write like this that we could not do otherwise. Now, if we want to find the tangent to a parametric curve, that is the tangent line, I should say, what I really need to do is find out what point do I want that tangent at. I still need to find out what the slope is and everything because I'm still looking for a line in the form y equals mx plus b. How am I going to find that slope? Well, in order to find the slope, we need to find dy over dx. That's a little bit difficult because y is not a function of x. So we've got a little bit of a trick here. Okay, this equation is really important later. Dy over dx I can find by taking dy over dt, taking the derivative of that y equation with respect to t, take the derivative of x with respect to t, so that should be dx over dt down on the bottom, and then dividing. So when I take dy over dt, I get 4 cosine t. I just followed my constant multiple rule, and I followed my rule for sine. The derivative of x with respect to t is negative 4 sine t. Again, constant multiple rule and my rule for cosine. Those two 4's cancel, and I get negative cotangent t. Now, I know I want this tangent line at the point 2 comma 2 square root of 3. That's an x, y point. I know that the t value that gives me that is pi over 3. How do I know that? I made this problem up. I know that my derivative is equal to a negative cotangent pi over 3, which is a negative 1 over the square root of 3. Obviously, I forgot my negative there. And now I just plug everything in. So I plug in my y minus y1. That's coming from the point where I want my tangent line. I want my slope to be negative 1 over the square root of 3. So m is negative 1 over the square root of 3. X minus x1, again, that 2 is coming from the point where we want the tangent line. So now, I need to go through and fix some signs here. This is a plus right there. There's my line. I'm not going to try to simplify it. This is actually my y-intercept right here. I'm not going to bother to try to simplify that. Let's just let it ride like that. We found our slope. We plugged it into the y minus y1 equals m times x minus x1. And we moved the 2 square root of 3 over. Just let it sit like that. If they were nice whole numbers or maybe nicer fractions, I may do a little bit of work. But let's just let it ride like that. Now, that really important equation that I want you to remember, that I also need to fix there, is this dy over dx is equal to dy over dt, the derivative of y with respect to some other variable. divided by dx over dt. Again, the derivative of x with respect to some other variable. We're going to use this later in the class. It's going to be a while before I'm going to refer back to this, but I want you to remember this because we are going to refer to this equation again, and I'm going to go, hey, remember that really important equation that I talked about back a while ago, dy over dt, blah, blah, blah. You need to remember this, okay? So I don't want you to sit there and go, no, I have no clue what you're talking about. Because yes, you do. Just make sure you write this down. Make sure you remember this. All right, so all that's left is for you to try some of this stuff on your own. I'll see you in class, and I'll see you online.